Hello everyone, in this video we will explore data environment in OpenMP including shared private, first private, last private and reduction variables. We will also understand critical performance issues like data race and false sharing with the practical examples. So let us understand what is this data environment and how it is going to useful in this OpenMP. And this in parallel programming, multiple threads run at the same time to perform the task faster and more efficiently. While executing these tasks, these threads often need to use variables and data. So the way these variables are defined, accessed, and shared among threads is known as the data environment. So the data environment determines mainly which variables are shared among all threads and which variables are private to each thread and how data is copied or updated during execution. The proper management of the data environment is crucial because incorrect sharing can lead to the race conditions and also incorrect results, unpredictable behavior. For example, if multiple threads modify the same variable without proper control, it may produce the wrong outputs, but defining the variables as a shared or a private programmers can ensure the safe and efficient execution. So the data environment is a key concept in parallel programming that controls how data is handled across the threads, ensuring both correctness and performance. So let us first understand what is data environment. So it defines mainly how the data variables are accessed, modified, and stored across threads. Let us dig little bit deeper to understand about this. What is a data environment? In parallel programming, multiple threads execute simultaneously and often need to work with variables. So the data environment refers to the rules and the structure that determine how these variables are handled across different threads. Like it defines access, like which thread can read or use variable, modification, like how and when the threads can update a variable, and storage. So whether a variable is shared among all threads or kept private to each thread. So based on the data environment, variables are typically categorized into the shared variables, private variables, first private, or last private. Like these are mainly to acts like share. If you take a shared variables accessible by all the threads, private variables are each thread has its own copy. First private or last private, these are the special cases controlling initialization and the final values. So properly defining the data environment is essential because it prevents the race condition and data conflicts and also ensure the correct and predictable results. It improves the parallel performance. So the data environment is a fundamental concept that controls the how data is managed in parallel program, ensuring the safe, efficient, and accurate execution across the multiple threads. So if you look at one by one in detail, like in this types of data environment in this OpenMP, and the first one is the shared. It is a variable. This shared variable is accessible by all the threads. all threads read and write the same memory locations. It needs a synchronization, that is to avoid the conflicts that we already understood in the previous lecture. Next one is a private. Each thread gets its own independent copy of the variable. So that is changes made by one thread do not affect others. So this is mainly used to prevent the race conditions. Next, fast, that is similar to the private. First private is similar to the private, but initialized with the original values. Each thread starts with the same initial value. This is mainly useful when the threads need a common starting point. And next one is the last private. So the last private, but the value from the last iteration of the thread is copied back to the original variable, which is mainly helps to retain the final output result. Next one is a reduction. This is used for operations like a sum, product, max, minimum. So each thread works on a local copy and results are combined at the end. Efficient or if this is mainly for efficient for the aggregation operations. So these data environment types can help control how variables behave across threads, ensuring safe and data handling, correctness, and improved performance in parallel programs. So let us see one by one in detail. So in OpenMP, a shared variable is one that is common to all the threads in a parallel region. So this means every thread can read and modify the same memory location. So when a thread updates a shared variable, the change is immediately visible to the other threads. So all threads work with the same copy of the data. If you look at the key characteristics, like mainly the single memory location shared across the threads, which enables the communication between the threads. So that requires the careful handling to avoid the conflicts. But there are some potential issues, like since multiple threads can modify the same variable at the same time, so it can lead to the race condition, incorrect or unpredicted results. So how we can avoid this? So to avoid this, synchronization techniques like critical automake should be used when updating the shared variables. And if you take one's example scenario, like if multiple threads update a shared counter without synchronization, the final value may be incorrect. That is using the a proper control ensures the accurate results. So shared variables are useful for data communication among threads, but they must handle carefully to maintain the correctness and consistency in parallel programs. And this is a program, like this looks like simple, but it causes a problem called as a data race that I will explain. And next one is a private variables. Like in OpenMP, a private variable means that each thread gets its own private variable means that each thread gets its own independent copy of the variable when parallel region begins. So these copies are completely separate. So changes made by one thread do not affect other threads. Like each thread has its own local copy. No sharing between threads helps avoid the race condition and data conflicts. And if you look at the behavior, like the initial value of a private variable is undefined, that is unless specified. Updates made by a thread are not visible to others. After execution, the original variable is not automatically updated. For example, let us look at this example scenario, like if a loop uses a private variable for calculations, each thread works independently, which ensuring correct and conflict free execution. So private variables are essential for maintaining the thread independence and data safety, which makes the parallel programs more reliable and efficient. And this is the code. You can just have a look. This like here, the each thread works independently without inference. This will be explained in detail in the uh, next lecture. So next one is a first private, and this is in OpenMP. First private class creates a separate copy of a variable for each thread, just like private. However, the key difference is that each thread's copy is initialized with the original value of that variable before the parallel region begins. And the key characteristics of this first private includes, like, each thread gets its own independent copy. The copy is initialized with the original value. Thus, changes made by one thread do not affect others. So why we use this first private? And that is a basic question we will get. So when all the threads need to start with the same initial value, and also useful for computations where the common baseline is required. For example, if you take like if a variable has an initial value, for example x equal to some 10, using first private of x ensures that each thread starts with x equal to 10 but modifies its own copy independently. Like after execution, changes made by threads are not copied back to the original variable. So first private combines the safety of private variables with the advantage of initial value sharing. So that makes it useful for consistent and independent thread execution. And this is the code related simple code, and that we will discuss in detail about this later. The next one is the last private. This is in OpenMP. This class is similar to the private, where each thread gets its own copy of a variable. However, it has an additional feature. So after the parallel execution complete, the value from the last logical iteration is copied back to the original variable. So each thread works with its own private copy. After execution, the final value, that is from the last iteration, is stored in the original variable. That is to mainly to ensure that the program retains the correct final result. So here the last refers to the sequential order of iterations, not the thread that finishes the last. So OpenMP determines which operation is considered the last logically. If you take an example scenario, in a loop running from I equal to 1 to 100, the value corresponding to I equal to 100 is considered the last iteration. So the last private ensures that this final value is saved back to the original variable. So last private is useful when you need to prevent the result of the final iteration, that is ensuring correctness while still benefiting from the parallel execution. And if you look at this simple code of this last private. And next one, reduction. This is mainly used in OpenMP. This class is used when multiple threads perform operations on a shared variables, such as sum, product, maximum, minimum. So instead of all threads updating the same variable, which can cause the conflicts. So each thread works on its own local copy. At the end of the parallel execution, all local results are combined, reduced into a single final value. The final result is stored in the original variable. So each thread gets a private copy of the variable. So no race conditions during the computation. final results is automatically combined. And the common operations we could perform is like a sum, product, max, minimum, logical operations, and or. And if you take example scenario like if multiple threads are calculating the sum of an array or the sum of 100 natural numbers, each thread computes a partial sum, and the reduction operation adds all partial sums to produce the final result. So reduction causes clause provides a safe, efficient, and convenient way to combine results from multiple threads, so that ensure the both correctness and high performance in parallel programs. And if you look at the code of this simple code, would look like this. So now let us understand about the data race and what we mean by this data race. A data race happens when the two or more threads simultaneously access a shared variable, and at least one of them modifies it without proper synchronization, because the thread execution order is unpredictable, so the final result becomes inconsistent and unreliable. So let us understand why the data race occurs. Mainly because of when the shared variables are accessed concurrently, so no synchronization mechanisms like a critical atomic or locks are used, and execution order of thread is not controlled. So what are the consequences of this data races? There are like incorrect results, unpredictable behavior, or difficult to debug and reproduce the errors. So if you take an example scenario, if multiple threads increment a shared counter, like for example, there is a variable counter, without synchronization, some updates may be lost, so resulting in a wrong final value. The counter, but the final value of a counter different every time. So how to prevent the data races? So here we use this critical sections, use atomic operations, apply locks or synchronization constructs, and we use the private variables where possible. So a data race is a critical issue in a parallel programming that can lead to the incorrect and unpredictable results, that making synchronization essential for ensuring data consistency and correctness. And this is the simple code of this race condition. Here the result becomes unpredictable. So next one is false sharing. How like our So these are the ways we can avoid the data races. Like we can use critical sections, use atomic reduction, or you can also use a proper synchronization. So next one is a false sharing, and this is mainly threads modify the different variables in a same cache line, and that causes the performance degradations. How we can avoid this false sharing? That is by using padding variables, align the memories, and use the private variables. So the data environment is critical in OpenMP. The proper usage avoids errors and improves the performance. So understanding races and sharing is essential here.